Let's let's switch gears just a little bit, and like in the past few minutes, I gave you an overview of the different kind of imaging methods that are commonly used. Now we'll get into like light and infrared optics. Okay, so before like I said, infrared optics, I wanted to give you like an overview of the fundamentals of optics that everyone should know. And some of these things may be elementary in the sense that you might have seen this before. What is a lens? What is a ray of light? And things of that sort. But I hope this lays a foundation for other things that we will discuss as we go along. Okay, so I wanted to start with ray optics. Okay, so the material here in the next few slides may be something you have seen before, but I want to provide additional context and show you the same thing that you have seen, but in a different way, so that you can appreciate it and kind of and understand this in first principles. Okay, so that's my goal for for the rest of the today. Okay, so ray optics is, so if you think of how to understand light, there are different ways of understanding light, and I like a quote from Einstein which says, "Make everything as simple as possible, but no simpler." Okay, so what does he mean by that? So whenever you're thinking of any like anything in nature, there you think of it in terms of models. Okay, model of this is my model. This is the way I like. This is the simplified version of the real. The world is really complex. I make a simplification and think about it in this simplified way. Okay, so there are different ways of simplifying thinking about light. Okay, if you think of the entire field of optics as this circle here, so like everything can be determined, like everything can be understood using quantum optics. Okay, that's the most general, and that's the widely kind of it's quantum optics, quantum mechanics, and quantum optics cover everything that you can understand in the world. It's way too complicated for most practical kind of doing quantum mechanical calculations is too hard and too kind of unnecessary for most things that we will encounter. Okay, then you have the next level down is the classical optics, the electromagnetic, the theories of Maxwell and kind of it's the synthesis of electromagnetic radiation, like things of that sort. So that's the next vector field kind of is basically electromagnetic optics, which is of course it's useful to understand things most it's simpler relative to quantum optics. It's simpler, but it's again still maybe too difficult in some situations. Then like further simplification is wave optics. Okay, I think this is kind of Huygens principle. If you remember from a long time ago, you have a sequence of dots, each emitting a spherical wave. A combination of these waves put together is what wave optics is all about. Okay, and then ray optics, the Newtonian, like thinking of light as particles, a stream of particles going bouncing around, that kind of a thing. That's kind of the most simple version of optics, which is kind of the easiest to understand in some ways. But of course, it does not explain the reason why people moved from ray optics to wave optics and to electromagnetics to quantum. There were problems. Ray optics could not understand diffraction, for example, and therefore it was insufficient. It was not a good enough model. It was good for some things, but not good enough for some things. Then you have waves can explain diffraction, but it could not understand some other things, electromagnetic kind of vector fields and so on. Electromagnetics could understand some things, but the quantum nature of light, so like quantization and things of that sort, the wave particle duality was things that could not be understood using the classical electromagnetics, and therefore you needed quantum optics. So there is a reason why each of these things were developed, and so currently accepted the broadest picture is quantum optics. But let's start with the simpler version. So that's why make everything as simple as possible, but no simpler. Whenever you you want to build a system, you use the simplest model of that model of light that is useful for you, which encapsulates everything that you understand and need to know about the system, but which doesn't introduce any complications. Okay, so if you use ray optics, for example, if you're dealing with X-rays, rays may be a good model for, although X-rays are electromagnetic waves, they have quantum properties, they also have vector properties, they also are waves, and but for the purpose of building an X-ray CT system, you don't need to understand diffraction of X-rays to build the system. Therefore, the simplest model is probably the one you want to use. And so make things as simple as possible in this hierarchy of things. But like if you want to consider diffraction, then ray optics is ineffective, and therefore it's you can't use that. So you have to go to the wave optics version. So that's essentially how you decide what model of light or what kind of how you think about the question, the problem that we are trying to understand. Okay, that's the premise of how we will think about light. Okay, so ray optics, some of you might have seen it like light. You have a point, it emits light, and like you draw lines, straight lines from emanating from that light source, and so on, right? So that's one way to like the kind of classical way of thinking about, old way of thinking about rays. There is, you can also think about ray optics from basically like in mathematics, you think of them as axioms, right? Starting from axiom. How many understand what axioms are in maths? Raise your hand if you axiom, geometry, axiom, Euclidean axioms, things of that sort. A few of you, not too many, but some of you. Okay, so basically, it's like a set of basic assumptions you make, and everything else is a logical consequence of these assumptions. Everything. So, like, yeah, so you have 2 points, and the shortest distance between them is a straight line. That's an assumption. Okay, a point consists of a bunch of dots. A line consists of a bunch of dots. Okay, so these are basic assumptions. Then from that you say, okay, the angles of a triangle add up to 180 degrees. Like that's a theorem which, logically thinking from these basic assumptions, you can construct the consequences. Okay? So for ray optics, there are some basic assumptions to make, and there are literally three or four of them. Okay, and but from that you can understand everything about ray optics from these assumptions. Okay, first is light travels in the form of rays, straight lines. Okay, when they reach the detector. Okay, and characterized by something called a refractive index, and refractive index is n equals c divided by c naught, where c naught is the speed of light in free space in vacuum, and c is the speed of light in that at that location in that medium. Okay, so basically it is proportional to the product n times d if there is a homogeneous medium. This is called the optical path length. Okay, so does it make sense? I want to just make sure we are on the right. So refractive index is this, like what is the speed of light in that medium? Like one divided like c divided by c naught. One divided by the speed, the relative speed in that medium. Okay. If the light travels slowly in that medium, the refractive index is high. Light travels at the same speed in the medium as in air or in vacuum, then its refractive index is 1. Okay, 1, 1.5, 2, like so. Basically, the higher the value of refractive index, the slower light travels in that medium. That's one of the assumptions of ray optics. Okay, and then if you have an inhomogeneous medium where the refractive index is changing from place to place, it's n is a function of position. Then this optical path length is the integral of the, like so if you have a path A to B, so you have one A here, B here. So you draw a line like this, a path of this sort, add up the refractive index here, here, here. Add this all, add up all the values of refractive index at every point, and that integration integration is just addition of small pieces, right? So addition of all these pieces is basically what is called the optical path length. Okay, that's the definition of optical path length. Yeah, and then you have the next and the last part, so to speak, which is what's called Fermat's principle, which says that light takes the shortest path. If it travels from point A to point B, it takes the shortest path, and that's it. Okay, with this assumption about light taking the shortest path, there is something called a refractive index, and there is something called an optical path, and you can, from this you can understand everything about ray optics. And everything is a logical consequence of these postulates. So light travels along the path that takes least time. So this is an argument from Fermat a long time ago, who basically said, let's say you light travels from let's say you have point A and point B. Light starts from here, reaches B. Light has to take the shortest path from A to B, because if it takes any other path, you can travel with the shortest path and reach there before light. And if you reach before light, that means you are traveling backwards in time. So you're going time will become negative. Time traveling backward, time traveling, and that's not possible. And therefore, light has to take the shortest path. It was his argument, but like whatever the kind of basis for his reasoning, the basic premise is that light takes the shortest time from go from place A to place B. Okay, and so with this, we can kind of understand a lot of things. So it means is that, let's say you have a point A, point B, there is nothing in between, like it's vacuum or air, right? So the straight line connecting the two is the shortest distance, and the shortest path, and therefore light travels in a straight line if there is nothing in between. That's one of the direct consequences. That's one of the logical. So you have the principles, the postulates, and the logical consequences of that postulate is that light has to travel in a straight line if there is nothing in between. Okay. The next question is, what if there is something in between? What happens? So we'll get to that in the next few slides. But so like you can see how you can understand why rays are straight lines from the assumptions. It takes the shortest path. Shortest path is a straight line. Therefore, it goes in a straight line. Okay. So that's how you understand that's the starting point for ray optics. Yeah. So the fact that light travels in a straight line has some important implications. What is it? For example, you have a point source. Light is emitted from a point, and there is an obstacle here. Because it travels in a straight line, then if you have a screen in the back, then all the rays of light which connect from here to this point A to any B1 and B2 and B3 and so on, draw straight lines. If there is nothing in between, then light reaches that point. You see like a bright light here. But if there is an object here which blocks the light, shadow. Shadows are a consequence of the fact that light travels in a straight line. Okay. Similarly, if you have a hole, if you have a light source, if you have a screen where you have cut a hole, circular hole, then light travels through it and reaches this side, and all the points in between, light reaches, and these other points, if you draw a straight line through, these are blocked by the screen, by this in between thing, and therefore you will get like this, like light in the form of the cutout here. If this is a square, you will see a square, whatever it is. Because you draw straight lines through, and you see what the shape is on the other side. And of course, this circle will be bigger than this because, again, it's a matter of geometry. Draw straight lines, the cone will become bigger and bigger as you go farther and farther away, the cross section of the cone. Okay? So, and another direct consequence is that, let's say you have light emitted in the shape of a the letter P. Okay. Now, if you have a pinhole, small hole here, then if you draw lines, what happens? And you put a screen on the other side. If you literally draw lines from every point here through the hole to the other side on the screen, what do you get? Get an inverted version of this letter P. Okay, imagine how this is the case. Just draw straight lines from every one point. So you have, let's say, an object of this sort. You have a hole here. Take any point in between here. Draw a line. It will be like this. Take this one. It will be like this, and draw a line here. It will be like this. So what you get in the end is basically an inverted version of the object here. Okay, so basically this is the principle of what's called a pinhole camera. So people figured this out a long time ago. I believe at least one of the reported versions is in the kind of in Egypt, when like there were pyramids, like sort of there was a hole in a tent, and on the like people could see on the other side of the tent, like on the inside of a tent, where it was dark, like people could see an inverted version of the pyramid kind of visible on the side of the screen, because there was a hole in the kind of one of the tent walls. And so basically they saw, okay, why is there an inverted version of the pyramid inside my kind of tent? And then they kind of started thinking about it and figured out that's kind of yeah. So but this is the principle of a pinhole camera. This is one of the ways in which you can think about light. So this is a direct consequence of the fact that light is, you can think of light as a sequence of a bunch of rays, and every point emits a ray and in all directions, and you draw a straight line and get the consequence. Okay. So the next thing is there are something called mirrors. Mirrors reflect light. Okay, so then you have the laws of reflection, and like how do you think about this question? Okay, so now light is reflected. So mirror is an object which reflects light. So now the question is, how does it reflect light? We can again go back to the principles, Fermat's principle, and kind of understand how this happens. Let's say you have a point A here and a point C here. Okay, now light can go straight from here to here. That's possible, but that's not interesting. That's not what happens if it gets reflected is what we are asking. Okay, so now let's ignore that particular possibility and let's look at the possibility that the situation when it hits the mirror and goes to C. Okay, it could hit the mirror here and then go to C here. It could hit the mirror here and go to C here. So the question is, let me use different colors to make it a little bit easier to understand. So it could take this path, it could take this path, it could take this path. So the question is, which of these paths will it take? Okay, so now how do you figure this out? Fermat says it takes the shortest look, measure the length here. What is the length from here to here and plus here to here, or measure the length from here to here and here to here. Add these two distances, minimize it, make it the smallest, which the light takes the shortest path, and it so happens that the shortest will be when these two distances are exactly equal. And so therefore one of the consequences is, if you measure the angle of incidence here, which is, or like there is a mirror here, draw a perpendicular and a ray of light hits this point, it can go in any different direction. It will go in a direction such that this angle here is equal to, this angle is called the angle of incidence, this angle is called the angle of reflection, angle of incidence is equal to the angle of reflection. So this is one of the, so yeah, so people discover this experimentally separately, but you can also think of it as minimizing its the shortest distance from point A to C, and through so you might, it's very likely that you've heard that angle of incidence is equal to angle of reflection, but you may not know why. And the why is it follows Fermat's principle of least distance or least time. Okay, so that's the basic idea here. Okay, so this is true of any kind of mirror. Mirror, I'm showing a flat mirror here. You can have a mirror which of any shape at every position. Basically, yeah. So so if there is a mirror here, and at every position, angle of like you draw a perpendicular at that location and get this, and you have light reflected. Angle of incidence is equal to angle of reflection. So at every point where light falls, you can have this kind of reflection, and you can construct the rays of light that come out of this. Okay, that's the ray optics way of thinking about reflection. Next, we go to the laws of refraction. So, so what happens? So in the first situation, we considered what happens when you have A and B, where everything is in air, where or in free space. Now, what if there is not free space? If you have, let's say, a medium, meaning something which has a refractive index which is greater than 1, and you're going from point A to point B here. So light could go this way, it could go this way, it could go this way, it could go this way. Which of these paths will light take? Yes, let's say it has to depend on the medium. Let's say the refractive index is n, meaning the speed of light here is c divided by n. Okay, so it's slower inside this medium by a certain factor. That factor is called the refractive index n. Okay, now of all the different possible paths that light can take, Fermat says it will take the shortest path. And in this case, because there is a medium here, it is not a straight line connecting the 2 points. So it's like, so you can, so there is a calculus way, how many of you have done optimization, classical kind of, how do you optimize, do some multivariable optimization? Like write it as a equation, differentiate it equal to 0, kind of minimize, and you can do the calculation. That I'm not showing you exactly how to do it. I'm trying to illustrate principles, and kind of I hope you can kind of get an intuitive sense for what it means. I can go through the math, but for the purpose of this particular lecture series, for understanding, like we will get to some equations that later. It's impossible to avoid equations. I just want to illustrate the principles so that you get a clear, intuitive understanding of how things work. And after that, we can go into some of the math and details. Math would not make sense without an intuition to start off. Okay. Yeah. So, the way to think. So you might have seen this n1 sine theta 1 equals n2 sine theta 2. Do you remember what this is? I can't. I didn't hear you properly. Snell's law. Yes, Snell's law of refraction. Right. So this is Snell figured this out experimentally a long time ago. But it turns out that the way to think about it is going from A to C here through where inside the medium of all the different paths. So like if you optimize it, it will be such that if theta 1 is the angle, this so this is the medium, like this is the boundary, draw perpendicular to the boundary. The angle this ray makes with the boundary, if this is theta 1, n1 is the refractive index on this side. n1 sine theta 1 is equal to n2 sine theta 2. is the path which the light will take. Okay, so there is yeah. So sorry. Yeah. So yeah. So basically, this Snell's law is also a direct consequence, like Fermat's principle of least time or least distance. So like if say the just think about it intuitively. If n is very very large, okay. So how do you go from one place to the other and to this? Okay. Um, so one way of like kind of to give you a completely different example which is analogous but not identical. So let's say this is yeah, this is land and this is water. Okay, this is like sort of out of like it sounds different. So you can walk on land and swim in water. And let's say swimming in water is slower than walking on land. And you're at point A, you want to get to point C. So which direction should you go? So that you walk and then you swim. And so you want to walk a little bit longer and then swim a little bit shorter, right? So if your swimming is very slow, the slower you're swimming, the farther you want to go on land and the shorter you want to go in water. If your swimming is as fast as you're walking, then you take a straight line. Exactly. Okay, so basically, depending on the speed in which of your swimming and speed of your walking, you basically, and it's the optimal way turns out to be where n1 sine theta 1 is equal to n2 sine theta 2. That's the direction in which you can go, so that you kind of use like that's the best shortest possible time you will take to go from A to C. And this is basically Slaz. Well, any questions about this? Okay. Yeah. So one of the another consequence of the fact that there is a mirror, if you have a point P1 which is emitting light, then light hits the mirror and reflects in all different directions. At each point, the angle of incidence is equal to reflection. And if you draw, so rays are coming out this way and light is traveling this way. So if you are standing here and looking at, if your eyes are here and you look from this direction, what will you see? You may not see the mirrors, you cannot see a mirror like the mirror itself unless there are defects on the mirror. It's like light is coming. What all you see is light coming towards you. You like that's you infer what is in front of you by the light that comes through your eyes, and you can that's what happened. So if you look at it will appear light coming this way will appear as though it's actually coming from this point P2, which is called a virtual point, a virtual object. For the it's indistinguishable. If you have a point source, which is light is coming this way, it is indistinguishable from if you have a point here and a mirror here, and light is getting reflected and light is reaching your eyes. Your eyes will see the exact same thing, and therefore you cannot distinguish this. And so this is called a virtual object. This is virtual emitter or virtual object here. So if you have a plane mirror, you will look at it. So by using the laws of reflection, like you will notice that like when you have plane mirrors, every point will have a virtual corresponding point on this side, which is basically it's a mirror image. In other words, this distance here is the same as this distance. Oops, sorry. Yeah, this distance over here. Okay, so that's the nature of this like these reflections. Oh, sorry, I forgot miss one other thing. Yeah. So if you have a parallel rays coming in, and if you have a mirror which is shaped just the right way, then it's possible to focus, like to have all the rays come to one point, and that is called focusing of light. And so the way to focus light, it so happens that if you use if this is a parabola, the shape is parabolic, then parallel rays will come and get reflected and come to one point, and that's called the point of focus. It's also, if you remember your like high school coordinate geometry, like all rays come from and come to one point, which is called the focus of the parabola. It's in fact the focus is the same word which is used in geometry as well. Okay, so this is in fact one way. This is so parabolic mirrors are used to get light to one single focus. Only parallel rays, parallel, which along the lines along this direction. So only if if light comes in along the parallel to the what's called the axis. So this, if there's a parabola, if you have a parabola, you have like the middle, like you draw a line through the middle. That's called the axis of the parabola. And so if the light rays are parallel to the parallel axis, then they will focus to one spot called the focus. Another thing is, if you have, instead of parabolic mirror, if you have like a sphere, like a spherical or a circular mirror, if you take a cross section, it looks like a circle, part of a circle, semicircle, part of a circle, then it's called a spherical mirror. And these are commonly used in a lot of optical experiments. You can use mirrors and lenses are some of the most common optical components which are used. And when it comes to mirrors, like these are called spherical mirrors, and you have just by using the laws of reflection and laws of, in this case, just reflection alone. So at every point, if you apply the laws of reflection, so angle of incidence is equal to angle of reflection, and you draw, like if you have a point emitter at P1, a ray goes here, reflects, comes here, and another ray goes this way and gets reflected and comes here. Another rays goes like this and comes here, and so on. So all these rays have to meet at one point, point P2, such that if this distance is Z1 here, and this distance, the location at which the point will form an image, or point will again focus. If light is emitted, where will they focus again? They focus somewhere at one point. Where will they focus? This position P2, which is at distance Z2, and it's such that 1 over Z1 plus 1 over Z2 is equal to 2 over R. The minus sign is there for a technical reason, but and this is this is called the position of the focus F. Okay. So R over 2 is like half this radius. R is the radius of the radius of curvature of the spherical mirror, and so you might have seen this kind of an equation long time ago, perhaps in high school or even beginning in first year or earlier, long time ago. Okay, so basically, so this is again a consequence of the fact that angle of incidence is equal to angle of reflection, and the surface is circular in nature. Okay, so 1 over Z1 plus 1 over Z2 is equal to 1 over F, like this. So this is the kind of this is the equation for these spherical mirrors. The next thing is what like. So I mentioned to you that if you have a medium and light goes through something which has through, like if you have a point here and another point here, the angle of n1 sin theta 1 is equal to n2 sin theta 2, right? So that's how light goes from here to here and here to here. So that this is Snell's law. Now this is the situation. So you go in this direction, and then light deviates towards towards the towards the perpendicular. A ray goes this way and comes towards the perpendicular. If the refractive index here is lower, then the refractive index here is higher. Okay, so if n1 is less than n2, then a ray comes this way and bends towards the perpendicular. But what happens if this side is higher refractive index and this side is lower refractive index? Then a ray comes here and bends away from the it deviates away from the perpendicular. In this case, so like this deviation is like, so because n1 sin theta 1 equal to n2 sin theta 2, this angle, the angle here will be larger, and as you increase theta 1, theta 2 will become larger and larger as well, and at some point theta will become 90 degrees. What does that mean? Light coming in here will basically, if it is, this is 90 degrees, it will travel literally along this surface. The ray of light which is falling on this surface will start traveling along the surface, and this is called total internal reflection. Okay, so this is the point where sort of light. So what is why is this kind of interesting? A ray of light typically coming in goes into the second, coming in from this medium goes into the second medium, right? What we are saying is that at some point light will stop going into the second medium completely. It will only come back towards the original medium. It will not cross this boundary. So it's almost like a barrier which prevents for these rays, for this ray and rays which are beyond this, light will actually not cross this boundary. It will remain on this side completely. So there will be no refraction, it will only be reflection. Okay? So all the energy that is coming in and hitting this boundary will get reflected. Total, complete internal reflection. It will not go, it will not be external, it will not go outside, it will not become external, it will be internal, total internal reflection. So basically it will stay inside the original place which started from. Okay, and this this is a very useful principle, because if you like, of course, total reflection was discovered more than 150 plus years ago, but it took so it all modern communication systems use what are called fiber optics, and fiber optics is based on this principle of total internal reflection. It took like till about 40 years ago or so for people to use the principle of total internal reflection to make a device, make something useful. There's this optical fiber, and this, like today, all internet, all communication, everything across the world goes through fiber optic cables, or at least high speed ones go through these cables. And the basic idea is you have a tube where there's a high refractive index and outside is relatively low refractive index. It could, and so basically when light hits the boundary, it stays inside this tube and it doesn't get out. And so you say, like, you have a long tube. I'm kind of using tube as a kind of general generic word. It's a piece of glass which is in the form of a cylinder where there is high refractive index on the inside, slightly lower refractive index on the outside. And if you send a ray of light into the middle higher refractive index area, light keeps bouncing around inside and it does not leave the fiber. So you can make this 1,000 kilometers and it will still keep going internally, getting reflected because total internal reflection, and send a sequence of pulses. You measure the pulses on the photons on the other side. That's communication. You have zeros and ones and kind of send light from one end to the other efficiently, and that's how you can communicate. Okay, so that's the basic idea. So this is the basis for total reflection. You can also make a prism. So normally you need a mirror. What is a mirror? You take glass, coat it with some kind of a metal on one side on the surface. It will act as a reflector. So we don't even, if you use total internal reflection, you don't need to put any metal coating or anything else. Just have angle, like this is at a 45-degree angle, say, light is coming in, because it's reflective, because it's more than this. So this angle at which this, so you have theta 1 equals to 2. So let's say N2 is air. So N2 becomes 1. And the sine theta 2, right? Theta 2 equals, so therefore sine theta 2 equals 1, right? So N1 sine theta 1 equals 1. Or sine theta 1 equals 1 over N1. Okay, what does this mean? The angle for some angle, depending on N1, at some particular angle, light reflects and it will not go into the second medium. So this angle theta 1, or it's called theta c here, it's also called the critical angle. So this angle theta 1 is sine inverse 1 over N1. And so for this particular, for any refractive index, there is a certain angle at which if light is incident, it will get totally internally reflected, and it keeps bouncing around inside, and you can build, you can make different kinds of, you can use this for, say, converting a prism into a mirror, or you are using it to make fiber optic cables, and so on. So the next thing is, so if you have a prism, okay, so this is, what is a prism? You take a glass, slice it into a triangle, like if you take a cross section of that, it looks like a triangle, and so basically it's like a wedge. Take a piece of rectangular glass, cut it in some way so that it becomes like a triangle in a cross section, and that's it's called a prism. And so light comes in, and so you can again use N1 sin theta 1 equal to N2 sin theta 2, and so on. So basically, if the refractive index of this prism glass is N, then you can figure out what direction the ray of light going in will come out at the other end. And so there are different kinds of mirrors, so there are all these components. I'm telling you this is, if you want to build an imaging system with light, you need to know what are the different kinds of available components at your disposal. So you can buy a spherical mirror, you can buy a parabolic mirror, you can buy a piece of glass which is like a triangle, you can buy a prism, in other words. You can also buy what are called partially reflecting mirrors. Okay, so this is another component which you can buy. So think of it as like you can buy components, put them together in a specific way, and create this new, like you have in your imagination, you have something you want to build, you put together parts to build that kind of device or an instrument or something of that sort. So have it available to you, partially reflecting mirrors. What do they do? Light is incident, some of the light is transmitted, some of the light is reflected. So this is something which is available. It turns out that this is very, very useful for building what are called interferometers. We'll get to exactly what they are in a little later, and they can be used for optical coherence tomography, building different kind of imaging systems. And you have your thin glass plate, and by the same token, you have beam combiners where light comes in this way, light comes this way. Both of them together will recombine into one beam, and one beam can be split into two beams in two different directions, or two beams coming in can be put together to make it one beam. So beam splitters and beam combiners are also possible. And then you have this concept of refraction at spherical boundaries. So, where we are heading is how to make a lens. That's really where we are going. Okay. Another optical component that's available to you is a lens. and a lens is something that focuses light to a small like region. And how does this work? Start with a situation where you have like a circular, so spherical surface. You have a point here, light comes in, refracts, and light goes this way. So angle of incidence is equal to angle of angle of n1 sin theta 1 equals n2 sin theta 2 in this case. Okay, so you can use the same Snell's law. You draw a perpendicular at that point, and you can use the Snell's law and calculate the direction of the ray that comes out. If you do that for all different rays here, this is one ray, this is another ray, this is another ray, it turns out that they all, under some approximations, they come and converge. One point, if it's emitting light here, all the different rays combined together again come to one dot over here. It's called a position of focus, and the equation that describes it. This, again, it's essentially, the way to think about it is again using the principle of Fermat's principle. So minimize the path that light takes, and you will know where the position will be. Okay, so like there is for rays which are getting emitted will come and converge to one point, and this particular equation will tell you how this convergence happens. If you take one spherical surface and take a second spherical surface, put them together, this is called a lens. And combination of two spherical surfaces, say if the radius of curvature is R1 here and R2 here, then the combined like what's called the focus. So if light is emitted from one point here, it changes direction and reaches another point here. The light's coming in, and so light coming from different directions will get kind of converges with this kind of converges with this kind of optical system called a lens. And it turns out that the way it converges is like, if you have a point P1 and you have theta 1, you can again use the same kind of equations that I mentioned here. And if Z1 is this distance and Z2 is this distance, 1 over Z1 plus 1 over Z2 is 1 over F, where F is basically this equation over here. Okay, so this is kind of, if you know this equation, and if you do the focal position of a lens, I'm sure, how many of you have seen this before? Most of you? Okay, good. So you have seen this is called the lens equation, and basically with this kind of an equation, you can figure out, if you have a lens, if you put an object in front of the lens at a certain distance, you can know where the image is, where the light being emitted, where will it converge. You can figure that out. And this is kind of useful for building imaging systems, as we will see. So this assumption that all the rays emitted will focus to a point is not always true. It's only true for light which is coming to the lens very close to, kind of almost parallel to the optical axis, this kind of to the middle of the lens. Light rays that are coming close to the middle will actually focus. Light which is actually going farther away, it turns out that they will not really focus to a point. In fact, the light rays coming here and here and here and here, all of them will focus to one spot. Like if you follow the path, they will all come to this one spot. But light rays that are coming here will actually will not touch this point. Light rays which are coming from So this will kind of come somewhere else here, and another ray of light coming here will kind of go this way, another ray will go this way. So there's a dot here, there is another dot over here. So only the rays which are what are called paraxial, which are very close to the middle of the lens, will get focused to a spot. So this assumption that parallel rays will come to one spot is a big assumption. It's assumption, one of the big assumptions of ray optics, and this is kind of a limitation. So if you want to, so if you buy a lens, you think, okay, it's a simple kind of take one spherical surface, like basically take a ball of glass, cut it, and you will get one sphere. Take another ball, cut it, put them, glue them together, you will get a lens. Perhaps one way to do it. It will work, but only if the kind of rays are very close to the middle of the lens. If the rays go farther away, then you will not get a good spot. Okay, so what do you do? How do you make all these other rays also come to the same spot over here? It can't be spherical. It has to be some other shape, and depending on the material here, you can optimize. People who work for Zeiss or who work for Nikon or who work for Olympus. There are companies who engineers. Their job is to figure out the exact shape of this surface, exact material here, such that they will focus to a spot. And people lenses can you can get a lens for $1 or $2, get a lens for $10,000 or $15,000, even $50,000. Believe it or not, you can get very, very expensive lenses. Difference between a cheap lens and a very expensive lenses. The expensive ones are such that they will give you, even for very high, large sizes, they'll give you a very small spot, almost like if you want to do very high resolution experiments, super resolution experiments, things which are difficult to do, and these are you will have to design these lenses in a way that it's a remarkable feat of engineering that you will get such a very good quality image. We'll get to why you need these kind of lenses in a different lecture on confocal microscopy, for example. I'll talk about that, but basically it's an art and a science in some ways to make these kind of lenses. This is the simplest version, which works well for most cases. But as things get more complicated, you will have to use wave optics and other things to get better quality focusing to one spot. Yeah. So there are. So you can basically you can use a sequence of lenses to propagate light in this way, or you can use total internal reflection. So reflection of this kind of boundaries in this way. So there are different ways in which you can propagate light and make light travel over large distances, and these are typically. So one good way is to do waveguide. So you can use lenses. A sequence of lenses you have is one way to transmit light, but you need a lot of these kind of lenses. Or you can use mirrors here, bunch of mirrors to reflect light, to take it from one place, to transmit light far away. This is called a waveguide, where you're confining light inside, and this is basically how an optical fiber works. Okay, so you have optical fibers where this is called the core, which has a high refractive index. This is called the cladding on the outside. It's a tube of cylinder where the cross section looks like this. Here it's high refractive index, here it's low refractive index, and basically you can calculate the critical angle at which light has to be incident so that it will remain inside. There is such a thing as an angle where once light gets in, it will not go out easily. The other advantage of optical fibers is that this, I've shown this as a straight line. It's like a rigid cylinder, but it can be flexible. So you can bend this, and still, as long as the angle of the incidence is greater than the critical angle, you still keep inside. And therefore, you can make this flexible tubes which can take light from one place to the other. Because it's used for first, it was optical communication, but one of the big advantages is that, like, sort of in medical imaging, we borrow a lot of things from other fields of science and engineering. What was first made for telecom, we use it for medical devices. For example, the new generation of optical coherence tomography, new kinds of medical systems, like it's handheld, you can kind of, if it's flexible kind of a tube, like you can move it and kind of make a medical device where a doctor can hold it and kind of navigate it. Because it's flexible, if it's a rigid thing, it will be hard to move. But you can make a flexible device, which would be otherwise hard to make. So optical fibers are used in medical imaging because they are flexible and they are easy to use and they're relatively thin. So they're not heavy and bulky. If it was like a giant metallic tube, because the the thickness of the hair, that's basically what. So this is something of the order of 125 microns, and this is of this depending on the wave that we'll get to the details later perhaps. So basically, fiber optics is quite commonly used, like because of its versatility and flexibility for different medical applications. So the last part I wanted to cover in the next few slides is what is called like sort of how to understand and how to like kind of just using ray optics, how to figure out how to building a more complex system. You have this system of lenses and mirrors and things of that sort. So how do you think about light propagation through, like if you just don't have one lens, but you have multiple lenses and a few mirrors and then a few more lenses and so on. When you have a complex system, how do you figure out, trace the path of the ray? Okay, so here this is called the ABCD matrix. So this is that literally have, so the way you define any ray is, take a point over here, its angle with, so there is something called the optical axis. So light is traveling, this is the z axis. So typically you have the kind of in this case x, y and z. Okay, so I guess let's use x, y and z or z. Okay, so you have the 3 dimensions over here, and so now a ray is traveling somewhere along this direction. The way you define a ray is you define it by its position. So the y coordinate, y here, and the angle theta, the angle that the ray is making with respect to, so let me erase some of this. So you define, so this point and the angle the ray makes with respect to the optical axis, y and theta. Y and theta completely define this particular ray at that location. So y theta is a ray, y1 theta 1 and y2 theta 2, for example. If a ray goes through a system, y1 theta 1, this ray comes out at the other. So y1 theta 1 comes in, goes through a bunch of lenses and mirrors, and y2 theta 2 comes out. So for example, a ray goes in like this and comes out like this. How do you define this transformation? What is it that the system does? Okay, so that is defined. The optical system can be defined by this 4 numbers, or A, B, C, D, or a matrix. So y1 theta 1 comes into the system, gets multiplied by this matrix, gives you y2 theta 2. So this A, B, C, D, or A, B, C, D tells you everything you need to know. Everything that's happening inside the optical system is characterized by these set of numbers. If you know A, B, C, D, It can maybe one lens, it may be a set of lenses, it may be a bunch of mirrors, lenses, everything. But everything in the end, one ray comes in. If you know for the one ray that comes in, what happens to the ray that comes out, then you understand the optical system. And that way you can characterize the optical system. So this is like this method. And so now you can imagine a ray coming in, goes through optical system, comes out. You can like this than that in the sense. So if you this like if you have a system where like kind of every small component, every component inside the optical system, you can define the ABCD matrix. This is for this kind of a system. We have this is the matrix. Basically, it's a displacement. It's literally light. It does not change direction. It's just traveling by a distance d. Here, like one because so the angle of like using Snell's law, and this ratio of this becomes n1 divided by n2. So this matrix tells you how the ray this becomes this ray. Okay, so basically this is how you can keep track of what is happening at every boundary. And so what you do is for every one of these simple components, you write the matrix. And when you put together a system, you put one lens, then a certain space, put another lens. So you know the matrix for lens 1, you know the matrix for the what's called free space propagation, how light travels from between one lens to the other. Then you have the matrix for the second lens. So you put together these matrices. Every of one reflection, you have the you know the matrices, and therefore lens, you put another transmission, put another lens, and so on. So each of these, as you put them together, you put the matrices together. And what you do is the overall effective matrix is M1 times N2 times M3 times M4. So the multiplication of all these matrices will give you the effective matrix of how the ray which is coming in will go out of the other end after all these things happen. So basically, if you know the matrix equation for every single component in between, you put them together, and that way, so as you like think of it as on a table, you're putting an object, putting a lens, giving some space, putting another lens, putting a mirror, then putting a say parabolic mirror, and then putting another lens, and so on. So you can literally trace the path of light. For each of them, you write the matrix, and you can write the final equation of the light that comes out. Given the light that comes in, you know the multiplication of all these matrices will give you the final answer for how the light comes out. Okay, so this way you can any complicated imaging system from small pieces. Okay, so that's the idea. Yeah. Mm-hmm. 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 Yes. That's an interesting question. Here, light, because of the nature in the ray optics, because of the nature of light, think of it as a photon going through. After it goes through, it doesn't come back. Or in other words, we are ignoring multiple reflections and things of that sort. What you're effectively saying is in optics will translate to there being multiple reflections. We are ignoring, like we are thinking that the photon going will keep going. It doesn't bounce back and forth. If it bounces back and forth, then the kind of complication you're talking about will arise. But the simplistic assumption of ray optics that we are talking about in this case assumes that it will go through. And like so, only under this simplification is what saying too. So what you said is correct. So if you, in the case of electrical system, you put a buffer in between, right, so that you disconnect the left side from the right side, and that way you can keep multiply them again. Take the transfer functions for each of them and multiply them. So that's the assumption we are essentially making over here as well. Okay. That's a good question. Let me pause here for today for today's lecture. Uh, like so, in the next class, I'll talk about wave optics and a few other. Like I'll continue our discussion of optics and kind of get into building more complicated systems and different other ways of understanding light. But for today, I want to stop here. This is a good stopping point. Any other questions about anything we have discussed here? Any questions online? No. Okay. Okay, then let's stop here. This kind of concludes my kind of discussion of ray optics. Like we'll get back to like imaging systems and how we can think of it as rays. But in the next, the tomorrow's lecture, I'll start with wave optics and what are the different. Like here, we have not considered phenomena like diffraction and interference and things of that sort. We are assuming rays of light just crisscross each other without like kind of having an effect on each other. That may not be the case. And when that's not the case, what happens? How to deal with them? What is the use? What are the advantages? What are the uses of situations of that sort? We'll discuss that in the next lecture. Okay, let's stop here for today. Thank you.